Swayam Prabha. Digital India. Educated India.
Alright, so welcome back. So in the last class we basically looked at the thermodynamics of phase transitions, and basically a very important equation that we wrote was known as Clausius-Clapeyron's equation, so which is del P by del T at constant V equals latent heat divided by temperature times Vf minus Vi, where the small v is the specific volume of the final phase and small vf is the specific volume of the final phase, and I stands for specific volume of the initial phase, right. So, during the phase transition. All right. And also two important other things that we saw were that so the second derivative of the specific Gibbs potential with respect to temperature in phase 2 at constant pressure minus dG1 by dt for the phase 1 at constant pressure, we saw that it came out to be L divided by T, and the derivative of specific Gibbs potential with respect to pressure on the other hand at the constant temperature minus dG1 by dP at constant temperature, that was the difference between the specific volumes of two phases. All right. And remember, when we are talking about phase transitions, we have such a typical phase diagram in our mind, which is of course experimental result essentially, right. So, people did experiments with the substance at various pressures and temperatures, and they came out with these phase boundaries, right. So, which looks something like that. So, at very high temperature you usually exist in a gas phase, at very low temperatures you exist in solid phase, and at slightly intermediate pressures you can even see a liquid phase, right. And we also discussed about the triple point, and I will talk little bit about this critical point today, right. And the way we characterize these phase transitions were for the first order phase transitions, our L was always non-zero. Okay. So, the first order phase transitions always require certain amount of latent heat for the phase to go from phase 1 to phase 2, all right. And also V2 minus V1 is also non-zero, right. So, their specific volumes also change, and what is specific volume? It is just the inverse of the density, right. So, the density, there is a drastic change in density of the substance as well as it undergoes the phase transition, all right. So, this is the first order phase transition, and we can also very readily see that since L is non-zero and V2 minus V1 is also non-zero, so their first derivatives across the phase point as you cross the phase boundary, they are also there is also finite jump, right. So, therefore, the first derivatives of the specific Gibbs potential, they are discontinuous, right. So, first derivative of Gibbs potential G is discontinuous. Okay. So, that is the reason this is known as a discontinuous transition or a first order transition, because in order to see the discontinuity we just have to take the first derivative. Okay. So, that is an easy way to remember this terminology. And the second thing that we did was second order phase transition, right. And this came from the observation that there are certain transitions where L is 0 and V2 minus V1 is also 0, alright. So, there are some transitions where there is no latent heat required and there is no change in specific volume or the density of the two phases, right. However, if we take the second derivative, basically second derivative of Gibbs potential with respect to temperature at constant pressure minus del square G1 by del T, del T squared at constant pressure. So, that is non-zero, alright. So, and we saw in the last class, I will not write down the entire expression, but this was proportional to the specific heat at constant pressure, and similarly the second derivative of the Gibbs potential with respect to pressure and difference of this quantity between two phases, that was proportional to, that scaled with isothermal compressibility, right. So, it is the second derivative which the difference between it is the value of the second derivative which differs between these two phases, right, and therefore, these are known as second order phase transitions, and second order because you have to take the second derivative of the specific Gibbs potential in order to see the discontinuity in the function, and we saw that in the last class, right. And these are also known as continuous phase transitions, right, because in contrast to first order phase transition, the first derivative of Gibbs potential, since L is 0 and V2 minus V1 is also 0, it is a continuous function, alright. So, I will quickly give you like very hand wavy example, right. So, we all know the first order phase transition, right. So, like if you would have a container of water or any liquid and you start heating it up, right. So, basically you start from somewhere here and you start heating it, you start increasing the temperature, you cross this boundary, right, and beyond certain point there is a clear distinction. So, what happens, your liquid suddenly goes into a gas phase, right. But the important point that I want to mention here is that during the coexistence, say you are sitting right here, okay. So, your liquid and gas phases can coexist. So, you will have a liquid phase and a gas phase, and the like I said, the underlying property of a liquid like we saw in the last class is the surface tension, right. So, therefore, there is a existence of a well defined meniscus at the interface of liquid and the gas, right. But now imagine I continue to move along this phase boundary, alright. So, what I am doing is I am increasing my pressure and temperature such that I stay along this line, but I reach this point, okay. So, what happens? So, okay. So, this is so say this is point 1, okay. So, this is what our condition is at point 1, but when we reach point 2, this is the point 2 which I also called as okay. But however, if you go to this point 2, okay. So, what happens, and this is an experimental observation. So, this meniscus becomes less and less well defined, right. So, and you reach a certain, okay. So, maybe I can draw an intermediate point also, say you are at point say 2 where your meniscus becomes, it's there, but it's barely visible, alright. So, meniscus is very thin, alright. You still have a distinction between liquid and gas. So, this is at point 2, but say you now move to point 3 which is the critical point, right. This is the critical point, then suddenly the distinction between liquid and gas phase just goes away, right. So, I mean you can't even make with the eye that where is the liquid phase and where is the gas phase, and this particular point is known as the critical point, okay. And the transition between this liquid to gas at this point 3, okay. So, maybe I can draw it. So, at point 3 the transition becomes second order, okay. However, when you cross the line either at point 1 or 2 or anywhere, the transition is first order. And if you continue to increase your pressure and temperature, say you come at point 4, then there is no transition because there is no distinction between liquid and gas phase, alright. So, so I just wanted to tell you this, that when you cross the solid line on the phase boundary, that is a typical first order phase transition, but when you cross a critical point, that is the second order phase transition. But if you go above the critical point, then there is no phase transition. Okay, so there is no distinction between liquid and gas phase anymore, and in more generally it is known as a fluid phase, right. Rather than calling it a liquid or gas specifically, we just call it a generic fluid phase. Okay. All right. So, all right, and again I can write few more things. So, like the generic phase diagram that we have, right. So, we have so this is temperature, this is pressure, this is solid, liquid and gas, all right. So, there are certain, so of course, like there are three transitions which are possible here. You can either go directly from solid to gas, right, or you can go to solid to liquid or liquid to gas, right. So, in the case of so let us start with maybe liquid to gas, right, and liquid to gas transition is a vaporization, right. So, you are vaporizing your liquid, and in which case the dP by dt, this is the Clausius-Clapeyron equation we are just rewriting. This is given by the latent heat of vaporization, right. So, this stands for vaporization divided by temperature of vaporization times the specific volume in the gas phase, which is the final phase, minus specific volume in the, let me write capital G perhaps, minus V L, right, and this is the liquid to gas transition, okay, and this is vaporization, essentially vaporization. Similarly, if we are at certain pressure and temperature such that the solid can directly go into gas, right, in which case we can write our Clausius-Clapeyron equation as this. So, you have, and this process is known as sublimation, right. So, for example, dry ice sublimates, all right. So, so dry ice is basically solid carbon dioxide, right. So, at atmospheric pressure it just goes into gaseous phase. Similarly, we have certain room fresheners which are in solid phase, they also sublimate, right. So, they do not melt, so they remain solid, but they over the time they just deplete, right. So, they also sublimate. So, these are like fragrances that we use, right. Okay. So, this process is known as sublimation, and temperature of sublimation times the final phase which is gas minus the initial phase which is solid, and this process is solid to gas transition, okay, and this is known as sublimation. And similarly, the third transition, this is dP by dt, this is known as, so solid to liquid is melting transition, right. So, this is L melting divided by T melting times V L minus Vs, right, and this transition is known as solid to liquid transition, and this is known as melting. Okay. So, these are all the first order transitions that are typically observed in any substance, any element, all right. Okay. So, okay. So, having said that, I will just talk about the phase diagram of water little bit, right. So, remember whenever I was drawing this phase diagram, I was being very careful in keeping the slope of this line positive, right. So, every time I drew this phase diagram, you must have observed the slope of the phase boundary which separates solid and liquid phase was always positive, right. But I will discuss a case where this is not true, okay. So, basically phase diagram of water, okay, and all right. So, let us look at this equation again, right. So, solid to liquid. So, dP by dt. So, for solid to liquid transition, so dP by dt equals L, and solid to liquid is melting divided by T melting times VL minus Vs, right. So, now I want you to turn your attention to this quantity, right. Now, so for most materials, okay, so for most materials, So density of liquid is always smaller than density of solid, right. So solids are much more densely packed atoms or molecules, right. So they obviously or they naturally will have a higher density than a liquid phase, right. So for most materials the density in a solid phase is greater than density in a liquid phase, right. And remember what is inverse of density, that is the specific volume. So this implies the specific volume in liquid phase is greater than specific volume in solid phase, right. And if you plug this which implies your VL minus Vs is positive, right. And if you plug a positive quantity in dP by dt, so as a virtue of that you always, okay, maybe I can draw this again. So you always get, okay, so you always get the phase boundary between solid and liquid, which has a maybe I can be little bit more explicit about it. So this has a positive slope, all right. So I will just draw it more clearly. So this has a positive slope, not that much, okay. So this slope is positive, okay. So the slope of this line separating solid and liquid is a positive slope, all right. But now let us come to water, right. But for water, for H2O, like which is water, we know that the density of liquid water is greater than density of ice, right. So that is why your ice cubes float on water, and it is due to hydrogen bonding and so on. I am not going into all that, but for water it's a very special substance, very special property it has, that the density of solid is less than density of liquid phase, right. And which automatically means your Vs is greater than Vl, or Vl minus Vs is negative, right. And if we put this negative quantity here, the slope of, so remember this is P and T, right. So slope of dP by dt of this line will become negative, right. So this is a phase diagram for most materials, most simple materials like argon, helium, right, simple materials, most materials. However, because of due to the fact that the solid is liquid is denser than solid for liquid water, for water, okay. So the slope of this line becomes negative, right. So you have liquid, you have solid, you have gas, okay. So the slope of this line becomes negative, all right. So this is one of the things which I wanted to talk about, that this Clausius-Clapeyron equation actually determines the boundary of these phase transition lines, all right. So that is why this Clausius-Clapeyron equation is very useful, okay. So so next thing that I will maybe quickly do is I will just take one example where we can actually quantify the shape of this boundary, and we will take an example of okay. So we'll basically work. So we'll basically solve the Clausius-Clapeyron equation around a triple point, and we'll try to get the equation of this curve which separates the liquid and the gaseous phase, all right. So basically what I am saying is, okay, so maybe I can say a few things. So say let us stick to maybe water, okay. So for water, like I said, this slope is negative and we have this special point which is known as triple point, right, and below this you have a solid phase, liquid phase and a gas phase, all right. And it turns out experimentally people have observed that the triple point corresponds to a temperature which is 0.01 degrees Celsius, and the pressure which corresponds to is 0.006 atmosphere, okay. So when you cool down your water to 0.01 degrees Celsius and decrease the pressure to 0.006 atmosphere, you can see the triple point where all three phases can coexist, okay. So let us write the Clausius-Clapeyron equation again. So dP by dt, and now I am interested in liquid to gas transition, right. So for liquid to gas, so this is L vaporization, right, divided by T vaporization times Vg minus VL, okay. Now we are going to make few assumptions, right. So let us assume that the moment liquid turns into gas, the density of the gas is much lower, right, and it is not a bad assumption, right. So when you boil water on a fire, right, so the liquid has much higher density, but as it turns into steam, the density of steam is much lower, right. So assume Vg is okay. So what we are assuming is the rho g is much smaller than rho L, right. So density of gas is much smaller than rho L, or this naturally implies that Vg is much greater than Vl, okay, which will imply I can rewrite this equation as dP by dt equals, so let me just write Lv for this, okay, Lv, okay, so Lv divided by Tv times Vg, okay. And we are going to make another assumption and also assume, so also assume H2O vapors, right, the steam behave as an ideal gas, right. Okay, under this simple approximation, we can write the specific volume as RT divided by P, right. So this is what we get, okay. And if we substitute it back, of course there will be a term of mass and all, but I am ignoring all that, right, because this is specific volume, this is volume per unit mass, right. So there will be term of mass, but I am ignoring all that. So so therefore so let's just so therefore if I plug this back here, so dP by dt becomes Lv divided by and this is basically RTV, right. So RT squared multiplied by P, all right. So this is what we get, and the third assumption that we will make is okay. So what we will do is, okay, so let me rewrite this. So this can be written as dP by P, dP by P equals Lv by R dt by T squared, right, and assuming Lv is independent of T, okay, if we make that assumption, so we can integrate this equation, right. So we can integrate this equation from, okay, so and let us say this point is T0 and P0, okay. So we are integrating this equation starting from here and moving to some other point, all right. So say we start from T0 P0, which is this point, to Tp, all right. So if we do that, so P0 to P dP by P equals Lv by R integral of T0 to T dt by T squared, and this is a very straightforward integral to solve. So this becomes log of P by P0 equals Lv by R times, so this will become minus 1 by T. So this is basically minus 1 by T plus 1 by T0, all right. And I can write my pressure final answer as pressure equals exponential of, so I am taking log, I am taking exponential on both sides, of minus Lv by R, okay. So I can replace this with the other bracket, times 1 by T minus 1 by T0. So I have taken the negative sign outside, all right. And you can very clearly see that, okay, so maybe I will do that again. So this is a line, okay. So maybe, okay. So remember our reference, okay. So since we are talking about water, so our reference point is this is T0 P0, right, and this equation is basically telling us how the pressure will increase, pressure will vary as a function of temperature close to this point, right. And you can see as I sorry, this should be temperature. So, as I increase my temperature, so this is pressure, this y axis is pressure. So, as I increase my temperature, all right. So, so as I increase my temperature, so this is a negative, so this P will also increase, right. So, there is an exponential of negative value multiplied by a value which is decreasing as T is increasing, right. So, therefore, this function will grow, right. So, basically what I am saying is, so this equation that we have derived in this blue box, okay. So, that basically represents the equation of this phase boundary which separates the liquid and gas phase, right. So, this is the equation, okay. So, this is the functional form of this equation, all right. So, this is how, by using Clausius-Clapeyron equation, we can actually quantify these phase boundaries by making some assumptions, of course, all right. So, this is how we can make sense of the phase diagram and the phase transitions that typically happen between liquid to solid to gas phase in various materials. So, we will now move on to a new topic which is known as chemical potential, okay. So, chemical potential. Okay. All right. So far, so let us go to first law of thermodynamics, right. So, from first law, we always wrote our first law as du equals dq plus dw, and we saw that this can be written as Tds minus Pdv, right. So, we said that we can change the internal energy of the system either by supplying some heat into the system or by doing work on the system, right. But you probably must have realized that I was deliberately always drawing these containers, these boxes which were always closed, right. So, therefore, the contribution to internal energy can only come from the external work that we are doing or the heat we are supplying, right. But now let us take the other case, right. So, what we can also do is, so rather than thinking about this situation, we can open this system, right. So, open system, right. So, there is no boundary to this system, right, or there is a leak in the system. So, in which case these particles can go in and out, right, and obviously that will also change the internal energy, right, and I will discuss about it why that should change the internal energy, right. So, therefore, so in case of open systems where particle exchange is allowed, so we can rewrite our first law as follows. So, your du basically becomes Tds minus Pdv, but now since the number of particles in the system which was n, which was constant before, right, that is, so the change in this n is non-zero. So, we have to add another quantity mu times dn, right, and this mu is basically the chemical potential, all right. So, okay, so this originates because of particle exchange, and how much energy will change by changing the by varying the number of particles in the system by an incremental amount dn, right. So, that will determine what is known as the chemical potential in the system, all right. So, before we go ahead, so I will just maybe physically or conceptually explain why this term originates, right. So, basically what is the origin of this chemical potential term, okay, and basically it arises because of intermolecular attractions, all right. So, the mu arises as a virtue of intermolecular attractions. Okay. And I will just take a very simple example. So, say we have a system, right, and it has certain number of particles, right, and say we open this system for a short while, so that there is another molecule which are sitting much farther away from it, and we are slowly bringing it back and throwing it into the system, right. So, we are changing the number of particles in the system, all right. So, remember these particles, they are typically interacting with each other, and the typical interaction potential like I have drawn many times looks something like this, right. So, this is R, this is your V, right, and this interaction potential is negative, right. So, there is a negative energy associated with this, all right. So, when this particle is sitting very far away, right. So, I can go to this page and draw this again. So, this is your R, this is your this is your potential energy essentially, right. So, this is the potential, let us just call it V, right. So, when the particle is very far, right, from other particles in the system, so at R equals infinity, right. So, we are assuming that the kinetic energy of this particle which we are planning on adding into the system, so the kinetic energy is 0, and also let us pick a reference that at R going to infinity the potential is also 0, right. So, the potential energy is also 0, all right. So, now let us bring this particle very slowly into the system, right. So, we are moving so slow that we can still ignore the kinetic energy of this process, right. So, and say so after some time we introduce this particle into the system and plug this hole, right. So, this is the particle which is now inside the system among many other molecules, right. So, and say it is at any given point, it is at a distance a away from its nearest neighbor, for example, right. So, after some time at R equals A, right. So, what will happen, right. So, imagine, so just see, right. So, our particle is at far away, right, it is at infinity, its potential is 0, but as we bring it closer, it basically falls down the potential well, right, and as a result it will gain certain kinetic energy, right. So, at R equals A, it will basically, so at R equals A, the additional particle or molecule accelerates down the potential well and attains finite kinetic energy, right. And there is still conservation of energy principle, right. So, if I sum up the total energy of all these molecules and this single molecule in isolation at R equals infinity, and when it is inside the system at R equals A, the total energy still remains same, right. But because it is falling down the potential hill, so this additional molecule will attain finite kinetic energy, and that will contribute to the internal energy of the system, right. And what is the amount of this finite kinetic energy that it attains? So, this kinetic energy at R equals A, which is positive, is exactly equal to the potential energy magnitude, right. So, this value essentially. So, this value, potential energy magnitude at R equals A. So, it's like, so you start with so you have a system, you open a channel, you bring a molecule in it, and because this molecule is attracted to other molecules in the system, it will fall down the potential well and it will gain certain kinetic energy. And if you keep on doing this process over and over again, and if you keep on adding more molecules in the system, so the total kinetic energy of this system will increase, and therefore its internal energy will also increase, all right. So, this is how you can make sense of how addition of molecules can increase the internal energy of the system, right. And the term that comes in front here, which I defined as chemical potential, so that just determines how deep is this potential well, right. So, if the molecules are attracting each other with much greater forces, there will be greater contribution to the internal energy, right. So, that basically tells you the magnitude of the chemical potential, all right. So, so let us go back to this equation again, all right. So, let us go back to this equation again. So, we saw that due to this additional chemical potential term, our first law becomes du equals Tds minus Pdv plus mu dn, And you can see that, okay, so you can see that in now the internal energy function becomes function of three natural variables: the entropy, volume and number of particles. And we can very easily see that in this case the chemical potential just becomes partial derivative of internal energy with respect to number of particles, while keeping the entropy and the volume of the system constant. All right. Okay. And of course, there are other definitions as well. So, remember we also defined Helmholtz potential, Helmholtz function or potential, right. So, this is f, which is u minus Ts, right, and I can again write the differential of s as, so du, which is Tds minus Pdv plus mu dn minus Tds minus Sdt. All right. So, some terms they will cancel out and we are left with minus Pdv plus minus Sdt plus mu dn. Okay. And in which case I can define my mu as the change in the Helmholtz function, Helmholtz free energy with respect to number of particles, while keeping volume and temperature of the system constant, right. And also from Gibbs function, which we define as G, which is u minus Ts plus Pv, right, in which case I can write my dg as Tds minus Pdv plus mu dn minus Tds minus Sdt plus Pdv plus Vdp, right. So, this will cancel out, Tds will cancel out and we are left with minus Sdt plus Vdp plus mu dn, in which case I can define my chemical potential as the derivative, partial derivative of Gibbs function with respect to number of particles while keeping temperature and pressure constant. Okay. So, I have written down three definitions of chemical potential and they are all equivalent, right. It just depends in what condition we are in, right. So, what are the natural variables in the process. All right. So, let us now try to understand again, like what does this conceptually mean, right. So, what is the significance of this chemical potential in determining the direction or the nature of a thermodynamic process. All right. So, let us talk about the condition of equilibrium, right. So, let us say phase equilibrium. Okay. So, say we have an isolated system. Okay. So, say we have an isolated system, it is not exchanging heat with surroundings. Okay. So, this is insulated. Okay. And say at any given point the system exists in two phases, right. So, there is phase A, which has temperature Ta, pressure Pa, volume Va, internal energy Ua and the number of particles Na, right. And similarly in phase B, the temperature is Tb, pressure is Pb, volume is Vb, internal energy is Ub and number of particle is Nb. Okay. And since this system is isolated, it is not exchanging anything with the surroundings. So, we know that at any given point Na plus Nb has to be constant, right. So, say this is N and this is a constant and this is basically conservation of mass. Okay. So, I can just write mass conservation. Similarly, its volume will also not change, right. So, these are say rigid walls, they do not change. So, Va plus Vb is also V, which also stays constant, and this is volume conservation. And also Ua plus Ub equals U also stays constant, and this is energy conservation. All right. Okay. And at thermal equilibrium, say the system is existing in thermal equilibrium at any given point. So, the condition for that will be, so in thermal equilibrium, in thermodynamic equilibrium, so the condition is that the entropy of phase A plus entropy of phase B, which is S, this has to be maximum, right. So, that is what we saw from the second law, that that in equilibrium the entropy of the system has to be maximum, right. So, now let us say in equilibrium there is infinitesimal change in these quantities, right. So, so while in equilibrium, right, so say N, U, V and S change infinitesimally, right. Okay. So, say they change infinitesimally, but the thermal equilibrium, but the equilibrium condition will still demand. Okay. So, then so that will still demand that the total change in entropy is 0, right. So, it is still at equilibrium, so it is at extremum, so its change in the total entropy is still 0, right, which implies dSA plus dSB is 0, right. So, this is at equilibrium, all right. And what we can do is we can write this infinitesimal change in the phase A as dUA, that will be given by so basically I am just okay. So, dUA, so this is just the first law applied to the subphase is to the phase A. So, TA dSA minus PA dVA plus mu A dNA, all right. And the change in internal energy of subphase B would be TB dSB minus PB dVB plus mu B dNB, okay. And from these two equations we can just write down the terms dSA and dSB. So, from these two equations we can write dSA. So, I am just dividing everything by temperature T and taking everything to the other side. So, this becomes 1 by TA times dUA plus PA dVA minus mu A dNA, and similarly dSB equals 1 divided by TB times dUB plus PB dVB minus mu B dNB, all right. Now remember so the total number of particles remains conserved. So, total volume does not change and total internal energy also does not change. So, therefore, I can take derivative on these equations. So, from conservation laws, from conservation conditions, okay, I can very easily check that dNA equals minus dNB, dVA equals minus dVB and dUA equals minus dUB, right. So, any change, so since total energy does not change, any change in the internal energy or volume or number of particles in phase B will be compensated by change in corresponding quantities in phase A, all right. So, therefore, I can so what I can do is, okay. So, now remember the condition in equilibrium is dSA plus dSB is 0, right. So, I can add up these equations, right. So, let us call this equation 1, let us call this equation 2. So, adding 1 and 2, so we have dSA plus dSB, which is equal to so dUA by TA plus dUB by TB, that is the first term, plus PA by TA dVA plus PB by TB, dVb minus mu A by Ta dNA, this is small n, dNA plus mu B by Tb dNb, right. And I can now replace dUA with minus dUB, dVA with minus dVb, and dNA with minus, and remember this is equal to 0, right. So clearly I can see that I can rewrite this as follows. So 1 by Ta minus 1 by Tb, I can write either of these quantities dUA for example, alright, plus Pa by Ta plus Pb by Tb, so there will be a minus sign actually. So minus dVA minus mu A by Ta minus mu B by Tb times dNA, this is equal to 0. Okay. So this is the condition, right, the condition for equilibrium. But remember the internal energy, volume and number of particles, right. So they are arbitrary independent variables in the problem, right. So they are all so they are all independent of each other. So therefore for this equation to be true, okay, so for this equation to be true, all these quantities, these factors which sit in front of dNA, dVA and dUA, they have to be independently equal to 0, right. So in equilibrium, so the condition for thermodynamic equilibrium becomes so 1 by Ta minus 1 by Tb equal to 0, which implies Ta equals Tb, right. The other equation is Pa by Ta minus Pb by Tb equal to 0, and since Ta and Tb are equal to 0, so Pa equal to Pb, right. And similarly, the most importantly, mu A by Ta minus mu B by Tb should also be 0, and again since Ta equals Tb, this implies the chemical potentials in both phase A and phase B have to be equal, right. And this equation, as we have already discussed, this is known as the condition for thermal equilibrium, right. So this is the condition for what is known as mechanical equilibrium, and this is the condition for diffusive equilibrium, all right. Okay. So therefore the two things that we actually already knew, for two systems to be in equilibrium, right. So two parts of the system to be in equilibrium, their temperatures have to be same, there should be no net force acting on the boundary separating these two systems, so pressures should also be equal on both sides. But the third quantity, right, which is new, which we just discussed, which is called chemical potentials, that also has to be equal to each other, all right. And I will okay, and we already know that from second law that heat flows from hot body to cold body, right. So say I artificially create a system where the phase A is at higher temperature than phase B, okay. So we know that heat will flow from A to B. Similarly, if I create the pressure on the phase A greater than pressure on the phase B, so the volume of the phase A will increase and volume of the phase B will decrease, right, because the system will expand towards phase B. But what do we mean by but what will it correspond to if we create a system where the chemical potential of phase A is greater than chemical potential of phase B, okay. So I am already giving you a hint, I called it diffusive equilibrium, but let us see what it means, all right. So okay, so suppose okay, maybe I can write here. So suppose we are far from equilibrium, right. So if we are far from equilibrium, that will imply that ds, the change in entropy, which is equal to, okay, maybe I can write in deltas now. So delta S, the change in entropy at that particular point, at that particular time, which is the change in entropy in subphase A and change in entropy in phase B, that has to be positive, right. So, if you are not in equilibrium, you must generate entropy until you attain a maximum entropy state, right. Okay. So, now consider a system, okay. So, and say okay, and say we are away from equilibrium because of some other reason, right, which has to which deals with the chemical potential, right. So, consider 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 there are excess particles in phase A and by amount which is delta N A, right. So, say there are more number of particles in the phase A than they should be in the equilibrium state, right, and say that quantity is delta N. Okay. So, therefore, the corresponding, and since the total number of particles remains constant, so there is a deficit of number of particles in phase B, right. So, the corresponding deficit of particles in phase B, that will be, let us call it NB, and that will exactly be equal to minus Na, delta Na, right, because the total number of particles remains constant, right. So, so say there are 5 extra particles in phase B, right. So, the deficit in B has to be minus 5, right, so that the sum is 0. Okay. Okay, and naturally now we can see that the natural flow of particles will be okay, so will be from A to B, right. So, as a consequence, so therefore, there will be flow of excess particles from A to B. Okay. And okay, so as a consequence, so therefore, and this would imply, so so this would result in, this results in entropy change in phase A, right. So, what will be the entropy change? So, that will be delta S A, right, and this is minus mu A by T A times minus delta N A. And how did I get this equation? So, I am using this term, right. So, the change in entropy contribution due to change in number of particles DNA is negative of, okay, so so let us ignore all this. So, this is minus mu divided by T times the change in number of particles, right. So, this is minus mu A divided by T times change in number of particles, which is minus delta Na, right. So, these particles are leaving the system. So, therefore, it acquires a negative sign, all right. And similarly, and also delta Na number particles, right, will enter the phase B, right. Okay. So, therefore, the associated change in entropy in phase B will be minus mu B divided by T B, and since it will gain number of particles, so there is a positive sign, all right. And let us now assume that the system is already in a thermal equilibrium as well as in mechanical equilibrium. Okay. So, if the system is already in thermal equilibrium, T A is already equal to T B. Okay. So, therefore, what will be delta S A plus delta S B, which we know is positive because system is out of equilibrium. So, this will imply mu A by T times delta N A minus mu B by T delta N A has to be greater than 0, and this implies mu A has to be greater than mu b, okay. And this is an important result, right. Okay. So what we have is, so we know that we have a situation, right, where there are more number of particles in phase A as compared to in phase B, okay. And we created a situation where we had an excess number of particles delta N A in phase B, and they were basically going from phase A to phase B, right. And the process continues until the entropy of the system becomes maximum, right. And but what we saw that this condition, this flow of particles the condition for this flow of particle is that the chemical potential in phase A has to be greater than chemical potential in phase B, and this is an important result, right, because we already conceptualized that the heat flows from hot body to cold body, right. So if you have a pressure in one part of the system greater than potential on the other, the wall separating those two parts will move towards the system with lower pressure, and the new quantity that we have defined, which is chemical potential, that assures that the particle flow, the excess particle flow is always from the region of higher chemical potential to the lower chemical potential, right. So therefore this is an interesting result, all right. So I think we can end the class today, and in the next class we'll continue developing few more concepts of thermodynamics. Thank you.